All righty. Good morning, lads and ladies. Welcome back to Calc 1. Flip over to the document camera here as people trickle in and we can get moving. Lecture. Today's date is the 2nd of April, 2021. Last time we talked about indefinite integrals and the net change theorem. Today I wanted to look at a handful of specific problems regarding the difference between net change and distance traveled, or net change and work done, or net change and amount of water pumped. These application problems from the end of section 5.4, they can be a little bit tricky. I'm not going to push you guys too hard here, but I do want to make sure that you understand the concepts and you're able to do the calculus operations related. So if you want physics, take a physics class. But here I will show you sort of the things that your physics professor will want you to know already. Sorry, it's chilly this morning, so this coffee is just especially pleasant. We're going to do more section 5.4. Specifically, first, like distance traveled stuff. Two L's in traveled. Okay. The other thing I'd like to do today, since this is not likely to take up the whole class period, is I want to introduce what is, you'll be glad to know, the last really challenging section, 5.5, which is on the substitution rule. For definite integrals. Calc 2 usually kind of begins, it's not supposed to, by the way, Calc 2 is supposed to begin with section 6.2, but Calc 2 usually kind of begins with professors seeing how well you understood this section. Strength in substitution is a pretty solid predictor of success in Calc 2. So spending a little bit of time on 5.5, I think it's wise, because that's going to be the main focus of next week's classes. And I just want to kind of get you ready for it. There are some things there that are a little bit hard to understand. There's quite a lot going on. So after we talk about 5.4 a little bit more, we're going to kind of prime you for 5.5. I'm trying to think if there's anything else. Let's see. I don't believe so. I don't believe so. We are pretty much there. After 5.5, we're going to cover 6.1. After we cover 6.1, we are done. Calc 1 is over. So after we finish 5.5 and 6.1, which will likely be next week, we'll start prepping for the final. Exam 3 is, of course, a thing, right? So exam 3 is going to be after we finish section 6.1. And the preparation for the final probably won't commence until after exam 3. So we knock exam 3 out early, we can spend a little more time prepping for the final. Or if you want to spend more time prepping for exam 3, then we will have less time to prep for the final. You can come talk to me in office hours, let me know how you're feeling about that stuff as we get a little bit closer to it. But let's go ahead and get into this. So I want to, there was a particular problem that we left off with on Wednesday. You guys are all committing this shit to memory, right? We're not ever going to let go of these crucial calculus facts. Here we go. So these are some examples of net change, right? If you have a function that's measuring the volume of water in a tub or whatever, then the derivative of that is how quickly water is flowing into or out of said tub. So, you pull the plug, V primed is going to be negative because the volume is decreasing because water is exiting. And it would be exiting at the speed of, whatever V prime is. If V prime is like -2 gallons per minute, then there's 2 gallons per minute dumping out of your tub. If V prime is +5 gallons per minute, then somebody is dumping 5 gallons a minute of water into your tub. And if you integrate V primed between two time values, you're going to get the net change in volume over that time interval. So it's going to tell you how much water you had at the start minus how much water you had at the end, or vice versa, giving you the change in the amount of water. So how much came in, how much went out. There's a handful of other examples here, like concentration of a chemical in a reaction. If you dump two chemicals that can talk to each other into a reaction vessel, then oftentimes they will, that chemical will go away. It'll react with this other motherfucker and form something else. So if you want to talk about the concentration, dCdt, the notation with the bracket here they're using is a notation from chemistry, but it's the same thing as C primed. Just like up here, we integrated V prime. If you integrate C primed, you'll get the net change in the concentration of those chemicals over time. You can play these games with other things too, like if you have density, you integrate density, you get net change in density, which is mass. If you're talking about population growth, you get the net change in population. So if I know that 10,000 people are moving to town every year or whatever, I've got some function that tells me the rate of change for population. I can integrate that to get the net change in population. The one I wanted to look at carefully here is this one from kinematics. This is the most famous, and this is the one that we've been sort of referring back to. So if S is your position and V is your velocity, then the integral of velocity from time t1 to time t2 is going to be the net change in position. And that's not always the same thing as the distance you've traveled. In particular, we see a lot of occasions, like in most of these examples up here, you think about the population is just increasing or the concentration is just going down, or someone is just pouring water into the tub. Usually the derivative is single signed in these problems, right? Usually the thing you're integrating is either always positive or always negative because the physical situation is just that way. But with velocity problems, with problems that have to do with kinematics, it's not at all uncommon to have the particle bounce left, right. So the velocity changes sign from positive to negative, negative to positive. And that means that the net change in position, which is what we call displacement, is not necessarily the same thing as the distance you travel. We talked about this last time. You can look more deeply at those notes. Remember we said that the integral of the absolute value, so this is where I'll pick back up. Recall. If v of t is the velocity of a particle moving along a straight path, from t equals a to t equals b, then the integral from a to b of v of t itself, this is equal to the displacement you could call this, I think I've been using the function x. I'll use the book's notation here, s of b minus s of a. It's how far you ended from where you started. Which if you're only traveling in one direction, is the same as the distance you travel, right? How far you ended from how far you started. If I walk east and I do nothing but walk east, then my displacement is how far I traveled. However, if I spend some time walking east and some time walking west, then my displacement would be less than the distance I traveled. If you want to get the distance traveled instead, you have to integrate the absolute value of the velocity function. This is equal to the distance traveled. And unfortunately, it's not as simple as saying it's just S of B minus S of A. That's just not true. But this is the distance you travel. And when you talk about arc length in Calc 2, you'll see a nifty connection between these two things, specifically when you talk about arc length for parametric curves. So let's look at a concrete example. This is a good one. They tell me a particle is moving along a straight line so that its velocity at time t is t squared minus t minus 6. Find the displacement and find the distance traveled. What was it? T squared minus t minus 6? Yeah. Find the displacement and distance traveled. We need a time interval from t equals 1 to 4. They say on the time interval, 1 is less than or equal to t is less than or equal to 4. Same thing. Same thing. In order to do this, get this out of the way. In order to do this, I want to draw a graph of v of t. I know that the displacement is just going to be the integral of v of t from 1 to 4. But the distance traveled is going to be the integral of the absolute value from 1 to 4. And in order to really understand this guy and how he relates to this guy, it's wise to graph the function we're integrating. Now, you guys are calculus students. We just had a test on curve sketching. This is not a hard curve to sketch. You don't need to do anything fancy. It's a quadratic function. Its graph is a parabola, completely determined by 3 points. And truthfully, if you know the two x-intercepts and you know the direction the parabola opens, in this case, it's going to open up because the lead coefficient is positive, you can draw for me a pretty good picture. So first, let's graph v of t. This guy factors nicely. Is t minus 3 times t plus 2. Amy, no thanks. Be a good boy. You can do this. Okay, so I can mark this as 3. I can mark this as -2. And we know when t is equal to 0, this thing is going to be down here at -6. So I'll mark this as -6. The actual vertex is a little bit further over here. It's going to be halfway between these guys. I'll mark that as like down here-ish. Oh, so then my curve should look something like this. Sorry. Curve should look something like this. And it doesn't have to be perfect, doesn't have to be beautiful. We want two things. The displacement, which from t equals 1 to t equals 4 should be the integral from 1 to 4 of v of t, which is the integral from 1 to 4 of, so always put your integrand in parentheses, t squared minus t minus 6 dt. And the antiderivative here is not difficult. Each piece follows from the power rule. So remember, you want to do an integral like this. You want to do any integral. Unless the problem explicitly tells you to use a Riemann sum, unless it explicitly tells you to use the definition of the definite integral, every other time you do a definite integral, from here on out, you use the fundamental theorem of calculus. You find an antiderivative, you plug in bounds. All right, I want that to be clear. I don't want anybody wasting time on the exam using a Riemann sum when they don't have to. You're asked to do a definite integral. Unless it tells you otherwise, find an antiderivative, plug in bounds, use FTC2. An antiderivative for t squared is 1/3 t cubed minus an antiderivative for t is 1/2 t squared minus an antiderivative for 6 is 6t. We evaluate this apparatus from 1 to 4. What we're finding here is this area. Right, that's what this integral is going to give us. This area down here, which will be measured as negative, and this area up here, which will be measured as positive. That's what this integral is going to give me. It's the integral of this function. This function is v of t. Do we expect this to be negative or positive?
Negative.
Good, yeah, look, the chunk of area beneath the x-axis appears larger. Let's see what we get. Or before I even move on, how would you interpret that physically? If this displacement comes out negative, which we expect it will, what does that mean about the physical situation? What does that mean about the particle's motion? Yeah, it means it traveled backwards more than it traveled forwards. Right? So let me be clear about this. This particle is traveling backwards here, 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 and then it turns around and it starts traveling forwards here, 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 and here. So this area is the distance it traveled backwards, and this area is the distance it traveled forwards. If this area is larger than this area, that means it traveled more backwards than it did forwards. Its net change in displacement is negative, which means its net displacement is heading backwards. All right. This is 1/3 times 4 cubed minus 1/2 times 4 squared minus 6 times 4 minus 1/3 times 1 cubed minus 1/2 times 1 squared minus 6 times 1. Four cubed is 64. So this is 64/3 minus 4 squared is 16. 16 halves minus 6 times 4 is 24. And then this is 1/3 minus 1/2 minus 6. Slide up. We can combine these taking our time if we want to. I might, just for sake of brevity, employ a calculator here. So this is 64/3 minus 16 halves is 8 minus 24. And then we'll have minus 1/3. Distributing the negative, we get plus 1/2. And then plus 6. We get negative 4.5 if you want that as a fraction. Negative 9 halves. So this is indeed negative. How on earth do I find the distance traveled though? That's where we really need the picture. So in fact, let me do it like this. First, are there any questions on the displacement integral? It's okay to ask. If there's anything you wonder in here, I'd like to hear it now.
Without looking at the graph, like if we didn't have a graph and we're just doing like numbers, would it always be the biggest number minus the smaller number?
Always upper bound minus lower bound,
Okay.
regardless of who is larger. So it's possible that this is the smaller number and this is the bigger number. So we always take whatever's up here, plug it in, and then subtract whatever's down here. You take your antiderivative, that's when the integral goes away. Right? You take your antiderivative, integral goes away. And then you have to plug in whatever this guy is, and then subtract whatever this guy is, regardless of who's bigger or smaller.
Okay.
It's a fair question. Other questions here? Now, we didn't really need the graph for this part, did we? Right? We could have just, when we did this computation, at no point did we have to refer back to the graph. But now if I want to do the integral for the distance traveled, get this back out of the way. The integral for the distance traveled that's the integral from 1 to 4 of the absolute value of v of t dt. And here I really do need the graph. I know that v of t is negative everywhere in here from 1 to 3, and that v of t is positive from 1 to 4. So recall the absolute value of some stuff, we'll call the stuff u, is equal to the stuff if the stuff is non-negative, and the negative of the stuff if the stuff is negative. So the absolute value of v of t is equal to v of t if v of t is positive, and it's equal to negative v of t if v of t is negative. In other words, we need to make sure we're counting this area as positive. but the regular integral will count it as negative. So there's a handful of ways to do this. You can do the integral from 1 to 3. All right, this is 1. You can do the integral from 1 to 3. That's definitely going to come out to a negative number. Just flip that number and make it positive, and then separately do the integral from 3 to 4. What that means is we would have negative integral 1 to 3 of v of t dt plus integral 3 to 4 of v of t dt. And that really is us using the definition of absolute value also. Think about it. This function is, the function inside the absolute value here is negative between 1 and 3. So the absolute value of that function is the negative of that function. Because if something is negative, you slap on another negative to make it positive. That's how absolute value works. And from 3 to 4, v of t is positive. So I don't need to do anything. I can just leave it alone. So this integral right here is measuring this area right here. This integral right here, without that negative sign, is measuring this area right here. Since this area we know to be all negative, the negative out front will make it positive. In other words, the absolute value of v of t is equal to negative v of t from 1 less than or equal to t less than or equal to 3, and it's equal to just v of t, 3 less than t less than or equal to 4. Right? Because that's how v of t works. V of t, this is why we needed the graph. We needed the graph to tell us what v of t is positive and negative. There's other ways to do this, but the graph is the simplest one. So this negative from 1 to 3 gives me this negative. And then the fact that v of t is positive from 3 to 4, I just do this. So we compute these integrals. All right. We'll continue down here. This is negative integral 1 to 3 v of t, which is t squared minus t minus 6 dt, plus integral 3 to 4 v of t, which is still t squared minus t minus 6. Is everybody on board with the setup? Are there questions about the setup? Sorry. Understand why we're doing the integrals we're doing and why it's split up the way it's split up? So here's the graph of v of t. Since v of t is negative from 1 to 3, everywhere between t equals 1 and t equals 3, v of t is itself negative. The absolute value of v of t there is negative v of t. If you take something negative and multiply it by negative, it becomes positive. And from 1 to 3, v of t is negative. Those are the v of t, remember, is the output, the y values on this graph. These y values are below the horizontal axis, which means they're negative. Because I want to integrate the absolute value of v of t, not v of t itself, I need to negate this to make it positive. So the absolute value of v of t from 1 to 3 is negative v of t. This negative makes the already negative function v of t positive. And then from t equals 3 to t equals 4, we're talking about this part of the graph, v of t was already positive. So from 3 to 4, the absolute value of v of t is just v of t itself. This integral measures the negative part of the area. So we slap a negative out front to make it positive. This integral measures the positive part of the area. So we leave it alone. That's the simplest way to do it. So I'm computing this area and this area separately. I know that this area is going to be measured as negative by the integral. So this integral right here, if I go ahead and compute this, I know it's going to give me like negative something, -5, whatever. I want to measure that area as positive. So I slap a negative out front to make this negative thing positive. Negative times -5 would be +5. And that means I'm going to measure this positive now, which is what I wanted. Remember, this was the distance I walked backwards. This is the distance I walked forwards. And I didn't want them to subtract from each other. I wanted the total distance traveled. So in order to get the total distance traveled, in order to avoid this being subtracted from this, I need to make sure I measure this as positive. The way to measure this as positive, since I know it's all negative, is to go ahead and crunch it out and then slap a negative out in front of it. So here's that area, which is beneath the axis. It would be measured as negative. This extra negative here makes it positive. Oh, well, they asked me to, yeah, I mean, we could integrate from -2 to 3 if we wanted, but remember the problem just said find the displacement and distance traveled from 1 to 4. So it's just answering the question that was asked. They said, I'm interested in times from t = 1 up to t = 4. That's just what they asked for. Alrighty then, let's do the integrals. The antiderivative step for each of these is the same as the previous problem because it's the same function. This is 1/3 t cubed minus 1/2 t squared minus 6t evaluated from 1 to 3 plus 1/3 t cubed minus 1/2 t squared minus 6t evaluated from 3 to 4. So here I'll have negative, run out of space on this line, I can see it already, 1/3 times 3 cubed minus 1/2 times 3 squared minus 6 times 3. And from that I need to subtract 1/3 times 1 cubed minus 1/2 times 1 squared minus 6 times 1. All of this is just this. So then I'll have plus 1/3 times 4 cubed minus 1/2 times 4 squared minus 6 times 4 minus 1/3 times 3 cubed minus 1/2 times 3 squared minus 6 times 3. And all of this is the second piece here. So I'll go ahead and crunch this, and then I'll crunch this separately in the calculator so we can keep kind of things straight, but don't lose too much time. Regular 4-function calculator is plenty to do this. On an exam, I will curate the problems to minimize the amount of arithmetic you have to do. I'm going to leave this negative out of the calculation for now. I'm just going to go ahead and crunch the thing in here. So that's 1/3 times 3 cubed. I suppose if I'm being good about this, I should put this in parentheses. Let me be good. Actually, how could I write this more neatly? This is 3 cubed over 3. We'll write it like that. Oh, goddamn. Right, so 3 cubed times 3. Good. Minus 3 squared over 2. Minus 18. And then we would have minus 1/3 plus 1/2 plus 6, distributing this negative. So the 1/3 is negative, the 1/2 becomes positive, the 6 becomes positive. All right, so everything in that first bracket is negative 7 1/3, or as a fraction, negative 22/3. So here I have negative bracket, negative 22/3, and then we're going to have plus, and what comes from the other bracketed statement there. Crunch that out. That's 4 cubed over 3, or 64 over 3. Minus 16 over 2, minus 8. Minus 24, 6 times 4. And then minus 27/3, or minus 9. All right, 3 cubed over 3 is 9. Plus 3 squared over 2, or 9/2. Plus 18. And this is 2.83333, and this is a fraction, you got 17/6. So this is 17 over 6. And what we see is what we expected, right? The first bracketed expression here is all of that negative area. That's why we had another negative out front ready to make him positive. And the second bracketed expression is a positive area, or a positive distance, and we don't need to do anything to him. So then this negative and this negative give me positive 22/3 plus 17/6. Why not? Having fun with Mr. Calculator this morning. 22/3 plus 17/6. Which is, oh wait, hang on. I was thinking that looked a little bit weird. 22/3. Didn't take the plus. Plus 17/6. Denominator looks a little big. Yeah. 61/6. So that's the distance traveled. Distance traveled should always be positive, right? Displacement can be positive, negative, 0, but distance traveled should always be at least non-negative. It's possible to travel 0 feet, but should never be negative. If we look at this guy, they split it up the same way. See here, from 1 to 3, they integrated negative v of t because they knew that v of t itself was negative from 1 to 3. So this extra negative right here makes it positive. And then you add that to your regular integral of v of t from 3 to 4. Computation is the same. They brought the negative in instead of waiting till the end, but same thing. Well, I didn't really change any pluses to minuses here. So remember what each of these represent. From time t equals 1 to t equals 3, my velocity was negative. I wanted to count this area as positive. So after finding this area, we multiply by a -1 to make it positive. This integral right here would be that area, and this negative is what's going to make this negative thing positive. You multiply negative by negative, and it will become positive. Is that the thing we're talking about? Help me out. What do you mean?
Okay, so I'm talking about the last part of it, like not the one with the, no, like on the third line.
Here?
Yeah, so on the first one, right? It's negative up front and negative in the middle, right there.
Yeah, there's a negative
No,
out.
not this one, the other one.
There's a negative here.
And there was a plus up there. That's
Okay.
what
So I distributed this negative over these terms. So the 1/3 here became negative, the 1/2 became positive, the 6 became positive. Is that what you mean?
no, because you see on the second line,
Here?
it was no, like up, go up.
Here.
Yeah, so this it was a positive. It was a positive, right?
So let me try matching up the pieces.
Yeah,
This negative is this negative.
right.
This bracketed evaluation expression is this whole thing.
Oh, and the other one
This plus
is
is
okay.
this
That's
plus.
okay.
Yeah,
That's what.
yeah. And this is this whole thing. Yeah, I
Oh.
just didn't have space. It wouldn't, I couldn't fit them both on the same line.
All right, that's what I was confused about.
I got you. I'm sorry about that. Yeah, so this expression here is this. This expression here is this.
I got it.
Cool. All right. Problems like these can be a little bit challenging. They can be a little bit fun. They can make for good kind of qualitative questions. Like here, I could ask you, if this is A1, A2, and A3, what would be the distance and what would be the displacement? The displacement would just be the integral, A1 minus A2 plus A3. And the distance would be the areas, A1 plus A2 plus A3. The idea is that the integral would measure this as negative. But if we want to measure distance rather than displacement, we need to measure this as positive along with those guys. So it would be wise, I'll say it one more time, it would be wise for you guys to read section 5.4. The other examples here are not anywhere near as important as the kinematics examples. But they're worth familiarizing yourself, especially if you intend to go into like chemistry, analytic chemistry at least. So yeah, that's that. Let's see, is there? I don't think there's anything else in here that I'm just dying to share with you. I have no desire to make you crunch out more Riemann sum shit at this point. You've had enough of that, and nobody does that down the road. Oh, we need an antiderivative. So yeah, this is the whole thing, right? All integrals from here on out, all definite integrals will be evaluated using FTC2. We need to find the antiderivative. This was kind of the big take home from Monday's lecture, is that calculating integrals is equivalent to finding antiderivatives. So you must find an antiderivative. A problem like this where you cannot find an antiderivative, you could attack through Riemann sums, but Riemann sums are frankly harder. So antiderivatives can be a bit of a chore, but yes, definitely we always do integrals as antiderivatives. Okay. The only other thing I really wanted to do today, guys, was to introduce 5.5. How am I doing on time? We got lots of time left. So maybe let's take just one more example of a definite integral that we can work on just for shits and giggles. Evaluate the integral here. So especially in view of that last question, let's see what we can do here. What looks like fun? Looks like 2 minus 2 over x, cute, but let's look at number 39 here. The integral from 1 to 8 of 2 plus t over the cube root of t squared dt. I'll write this down and then we'll pan back. Integral 1 to 8, 2 plus t over the cube root of t squared dt. Here we go. We'll do one more like this before we talk about substitution. Like I was just saying, all integrals are now done by finding antiderivatives. That's the game. How could I go about finding an antiderivative for this thing? This looks a little bit complicated. Any ideas here? Yeah, I think Trevor's idea to rewrite the downstairs as t to the 2/3 is a really good idea. So let's start with that. This is integral 1 to 8, 2 plus t over t to the 2/3 dt. All right, we know from our algebra classes that the cube root is a 1/3 power. So this is t to the 2 all to the 1/3, which is t to the 2/3. What can I do from here?
Move the t to the 2/3 up.
I suppose we could do that. Since both Mackenzie and Trevor are leaning in that direction, we can do it. Remember that these fraction bars imply parentheses. So if you're going to bring that t to the 2/3 up, if that's what feels right to you, we can do it that way. Just make sure you put the 2 plus t in parentheses, and then this would become what? T to the, what will this piece be as I move it up?
Negative 2/3.
Yeah, t to the negative 2/3, and then my dt is chilling. All right, what now? Oh, my door's open. Be right back.
No, you would distribute. Oh.
Yeah, we can distribute the t to the negative 2/3, and we must. Right, just like you can't differentiate products by differentiating one piece at a time, you can't anti-differentiate products. I can't like take the antiderivative of this and multiply by the antiderivative of this. That shit never works. But if we distribute this, then we can handle each of those pieces separately. So this is integral 1 to 8, parentheses, 2t to the negative 2/3 plus t times t to the negative 2/3, close parentheses, dt. And still, I can't integrate this piece. Still, I need to do something else here. What do I need to do here?
Wouldn't that turn into t raised to the 1/3?
Yeah, this is t to the 1 times t to the negative 2/3, which is t to the 1 minus 2/3. So remember, t to the a times t to the b is t to the a plus b. So t to the 1 times t to the negative 2/3 is t to the 1 plus negative 2/3, which is t to the 3/3 minus 2/3 is 1/3. So we still haven't done any calculus. We're still just doing algebra, but that's good. Algebra is our best friend. This piece is still 2t to the negative 2/3. And then we have plus t to the 1/3, and then dt. Okay, now I'm ready for an antiderivative, right? Because now I've got two pieces, each of which is simple to find an antiderivative of, and they're separated by addition only. So I can take the antiderivative of this separate from the antiderivative of this. The 2 will come along for the ride. T to the 2/3, or t to the negative 2/3. We need to add 1 to that power. So what is negative 2/3 plus 1?
1/3.
Positive 1/3. And then we'll divide by that new power. All right, that's our power rule for antiderivatives. Add 1 to the power, divide by the new power. And then over here we have plus. Same game. We'll have t to the, what is 1/3 plus 1?
4/3.
4/3. And then I divide by 4/3. And all of this is to be evaluated. Notice when I take my antiderivative, two things happen. The integral and dt go away, right? Those vanish, but I have these evaluation brackets. And again, most of the places where you could make a mistake here are little algebra things. Be mindful of your order of operations, be mindful of how to divide fractions. Dividing by 1/3 is the same as multiplying by 3. So I would clean this up before I proceed. This is 6t to the 1/3 plus 3/4 t to the 4/3 evaluated from 1 to 8. Now I need to plug in 8 to this apparatus and then subtract what I get when I plug in 1 to this apparatus. So this will be bracket, parentheses, 6 times 8 to the 1/3 plus 3/4 times 8 to the 4/3, close parentheses, minus 6 times 1 to the 1/3 plus 3/4 times 1 to the 4/3, close paren, close bracket. What is 8 to the 1/3?
2.
Good, yeah, remember 1/3, sorry, is the cube root. And 8 is 2 cubed. Okay, so 8 to the 4/3 would be 8 raised to the 1/3, all raised to the 4. 8 to the 1/3 of the cube root of 8 is 2, and 2 to the 4 is 16. Yeah, good. And then 1 to any power is 1. So this is minus 6 plus 3/4. So here this is 12. 16 divided by 4 is 4. 4 times 3 is 12. This is 12 plus 12. I need an open print here. So this is 12. This is also 12. So that first piece is 24 minus 6 as a ratio over 4 is 24 fourths. Right? Yeah. So 24 plus 3 is 27. So this piece here is 27 fourths. And if you want to put those together, you could. 24 times 4 is 96. And 96 minus 27. We're having a calculator day today. It's Friday. My arithmetic skills are probably worse than yours. $69 fourths. For the purposes of a test, just so we're clear, especially if you didn't have a calculator with you, you're not allowed graphing calculators, right? We know that. But you are allowed the TI-30, which is capable of doing all the arithmetic that I've done here in class today. But if you didn't have a calculator with you, you could stop here. I would like to see you get it here, at least. but I don't want you burning time on a test doing arithmetic. So if you get to here and you're like, I don't want to waste time figuring this fraction out, that's okay. All right, I do trust at this point that you can do arithmetic given time. All right. The other thing I wanted to do for you guys today was introduce section 5.4. So before I move on to that, are there any, introduce section 5.5. Are there any questions on this example before we go to that? Okay then. All right. I'm hoping that the kind of mental place you guys are in right now is one of relief. No more Riemann sums. Now that we have the fundamental theorem of calculus, we can evaluate integrals the nice way. Antiderivatives, so far, not so bad, right? And there's some memorization, but it's not the end of the world. And it luckily is shit that you already know, just kind of in the other direction. You know how to take derivatives. So every derivative, you know, just read backwards is an antiderivative. But I invite you to ponder the following. Let's say from 1 to 2 of the square root of x minus 1 dx, or the integral from 0 to pi over 4 of the sine of 2 theta d theta. In theory, if you wanted to, you could set up Riemann sums for these. But like I said earlier, no more Riemann sums. You don't want to do it, and it's not nice. And when you get down to it, the Riemann sums for both of these aren't going to be things you can compute nicely, because you won't get a nice summation formula for the square root of anything or the sine of anything. But also, these don't fit into any of our known antiderivatives. Why do these not fit into any of our known antiderivatives?
Because they're both functions.
Yeah, they're definitely both functions, but all the things in our known antiderivatives are functions. Specifically, what kind of functions are they? It's a particular word I'm looking for here. Starts with a C. Ends with composite. They're composite functions, right? If this was just the square root of x, I know what to do with that. That's x to the 1/2. But this, square roots don't distribute. This is not x to the 1/2 minus 1 to the 1/2. That shit never works. And similarly over here, if this was just sine theta, then I would know what to do. But it's not sine theta, it's sine of 2 theta. So this has an inner function and an outer function. This has an inner function and an outer function. If you were differentiating instead of integrating, you would use the chain rule. We have a backwards power rule. Wouldn't it be nice if we had a backwards chain rule? That's what we would need. That's precisely what we would need here. I'm going to begin with this example. So this is our little intro to 5.5. And remember what I said earlier, this is kind of the last really challenging section. I want to begin just by thinking in terms of pictures. If you had an even halfway decent pre-calculus class, you should be able to tell me what this function looks like. I'm not going to put anybody on the spot, but I'll remind you that the square root of x is like a half of a sideways parabola. So the square root of x minus 1 should be that same half of a sideways parabola shifted to the right by 1 unit. This is y equals square root x minus 1 like this. We have a vertical tangent line here at 1. When x is equal to 2, the height here should be 1. And that's what we want. We want the area. I'll shift this out actually a little further. Why not? Call this 2. What we're looking for here is the area from 1 to 2 under this square rooty fellow. And let me also draw the graph of good old-fashioned root x. I'll draw that in blue. Try to draw it to the same scale. Square root of x. Maybe here I'll mark 1. And I'm going to shade an area here. Now, what did we say? I said that these are the same graphs, right? It's just that my function has been shifted to the right 1 unit. If I shift this bad boy to the right 1 unit, it becomes this. So do you believe me when I say the two shaded areas are the same?
Yes.
Yeah, they better be, right? So here's how you do this, which is this. You transform it into this. But the catch is, you don't want to use the same variable. So instead of calling this x, I say, hold up, I'm just going to call this the square root of u. I'm going to call this the u axis. You make what's called a change of variable or a substitution. And they can be much deeper than this. This is sort of the simplest kind of substitution, a translation. A substitution is a change of variables, or in terms of the picture, it's a change of coordinates. So here's how this looks. I have integral 1 to 2 square root of x minus 1 dx. And I say I'm going to substitute sub u equals x minus 1. That's helicopter flying. I choose to substitute for x minus 1 because that's kind of my inner function. I'm looking for an inner and an outer. And I say, okay, well, if I didn't have this inner, if this was just u, square root of u, that's something I know how to handle. Every time you make a substitution, you need to immediately calculate the differential. Remember differentials? Way back when we talked about linear approximation, we also talked about what a differential was. And I said, we're going to use this later, but we're not going to stress about it here. Here is the later. du is the derivative of x minus 1 times dx. The derivative of x minus 1 is just 1. So du is 1 dx. I'll show you why this matters in our next example. The other thing you need to do, since this is what's called a definite integral, remember it's an integral with bounds, anytime you make a substitution in a definite integral, you need to change the bounds. So bounds. When x is equal to 1, u is equal to 0, right? If I plug 1 in for x here, then u would be 1 minus 1, which is 0. And when x is equal to 2, u would be equal to 2 minus 1, which is 1. And that's the 0 and 1 you see here in this blue picture. So to get the same area as I do under this graph from 1 to 2, I need to be looking at the area from 0 to 1 under this graph. So these are the old bounds, these are the new bounds. And I can say now that this integral is equal to the integral from 0 to 1, the square root of x minus 1 just becomes the square root of u, because u is x minus 1, or because I know I'm looking for the area underneath root u. And dx and du are equal to each other, right? 1 times dx is just dx. So because dx and du are exactly equal to each other, this just becomes this. And now imagine I gave you this problem at the start instead. You know how to do this one. This is one that you know, you've had something like this in your homework. So substitution is a change of coordinates, a change of variables that takes you from an integral you don't know how to do to an integral that you do know how to do. Makes your antiderivative easier. It really is a backwards chain rule. And this is sort of the inner part of the chain rule. This is where things can get a little bit complicated, is with the du's and dx's. I'll show you another example in just a second. Let's go ahead and crunch this out though. An antiderivative for the square root of u, remember this is integral 0 to 1, u to the 1/2 du. So an antiderivative there, we would add 1 to this power. We get 3/2. This is u to the 3/2 divided by 3/2. And you evaluate it between these new bounds, right? You just pretend like this is the whole problem now. So 0 to 1. That's the same as 2/3 u to the 3/2 from 0 to 1. And so that gives me 2/3 times 1 to the 3/2 minus 2/3 times 0 to the 3/2. And 0 to the 3/2 is 0. 1 to the 3/2 is 1. So this is just 2/3. I want you to take a second and appreciate what happened here, because the integral we started with, we didn't know how to do. The picture is helpful in understanding why it works, but the mechanics of how it works is all right here. So we take this integral. We chose to substitute for the piece under the radical. It's a fairly common move. So we chose to substitute u equals x minus 1 because x minus 1 was under the radical. U is a new variable that I get to pick. Right away, we calculate du. In this case, du was equal to dx. You do this just by differentiating. So whatever goes here is the derivative of this thing. All right, u becomes du when you differentiate. X minus 1 has derivative 1. So you can think of it like du over dx is equal to 1, and then multiply both sides by dx, but we shouldn't. right? The multiply by dx is a little bit of a silly thing to say. That's why we talked about differentials earlier. Try and get around. Then you need to change your bounds. To change your bounds, you just plug the old bounds, which were 1 and 2, into the substitution for the old variable. So my old lower bound was 1. And if I take x equals 1 and I plug it in here, I get u equals 0, right? U equals 1 minus 1, which is 0. So my old lower bound was 1. That leads to a new lower bound of 0. Similarly, if I take my old upper bound, which was 2, say, okay, when x is equal to 2, what is u? Well, let's come over here. I'm going to plug 2 in here. When x is equal to 2, u is equal to 2 minus 1. Well, 2 minus 1 is 1. So the old lower bound of x equals 2 leads to the new upper bound, u equals 1. So you choose your substitution, calculate your differential, change your bounds, then plug everything in. Dx became du because du and dx are equal. Integral 2 to 1 became integral 1 to 0 because those were how my bounds changed. And the square root of x minus 1 became the square root of u. And now this is an integral I know how to do. I'd like to look now at the next integral. Sine of 2 theta from 0 to pi over 4. Sine of 2 theta is like sine theta, but it's compressed by a factor of 2. Let me show you this in decimals, it'll be easier. Yeah. All right. And the region I'm looking for here is from 0 to pi over 4. So there's pi over 4. All right, here's the region in question. What does this remind you of? If I didn't tell you that this was sine of 2x, these look pretty similar, don't they? Here's my region, and here's the kind of similar region bounded by the regular sine function. But they're not exactly the same. It's not like the last one, where those two areas are exactly the same. In fact, what's going on is this is exactly 1/2 of this. They have the same shape. This is just scaled up larger. So the purple is twice as large as the blue. But it's going to take a minute for me to show you that. If you trust in the procedure, though, it will work out fine. Again, I've got a composite function here. My outer is sine, my inner is 2 theta. So I would like to sub u equals 2 theta. because I want to integrate just sine of u. I know how to do that. I don't know how to integrate sine of 2 theta. This time du is not just d theta. If you differentiate on both sides here, you get u primed or du on the left. On the right-hand side, the derivative of 2 theta, just like 2x, is 2. So du is 2 d theta. And that's that doubling I mentioned. We have to change the bounds. When theta is equal to 0, I plug 0 in for theta here, u would be equal to 2 times 0. Well, 2 times 0 is still 0. And when theta is equal to pi over 4, u would be equal to 2 times pi over 4. Well, 2 pi over 4 is pi over 2. So this is how this works. And now, just like before, I have a new integral with new bounds, 0 to pi over 2. Sine of 2 theta, well, 2 theta is u. So this just becomes the sine of u. The interesting thing here is that d theta is not equal to du. We differentiate. We differentiate. So the derivative of 2 theta is just 2. So the differential du is 2 d theta. But yeah, we really just differentiate this. The left-hand side will become du, and the right, we always have a d theta. But what goes in here is always just the derivative of this thing. Since du is equal to 2 d theta, I'm trying to plug in for d theta here. So I'm going to solve this for d theta. We see that 1/2 du is equal to d theta. Right, just divide both sides here by 2. Then you see that d theta, this piece that I'm trying to replace down here, isn't just du, it's 1/2 du. So in the past, when I was harping on you guys to write your differentials at the end of the integrals, I said, don't forget writing dx, always write this thing, even though it matters. I'll tell you why it matters later. This is why it matters. If you want to think about this as widths of rectangles, the idea is as you go from one coordinate system to the other, the rectangles all get chopped in half as far as their width is concerned. Right? If I want to take the same system of rectangles for the purple here and transform it into a system of rectangles for the blue here, I would have to cut the width of each rectangle in half. So your d theta, the rectangles in the original coordinate system, would be cut in half in width. And that's why you have a 1/2 du here. But now, again, you can treat this like its own fresh problem. That 1/2 is a constant multiple, it can come out. And I get 1/2 integral 0 to pi over 2 sine of u du. So like I said, the original problem is 1/2 of the area bounded by the normal sine function from 0 to pi over 2. We know how to find an antiderivative for the sine function. The derivative of cosine is negative sine, so the antiderivative for sine is negative cosine. And the variables matter here, right? Don't forget to write the variables. It's sine of u, so this is cosine of u. The 1/2 came out, we need to evaluate between bounds. If I plug in pi over 2, let's just do it. This is going to be 1/2 negative cos pi over 2 minus negative cos of 0. Cosine of pi over 2 is what? What is this? for our unit circle. Zero. And the cosine of 0 is 1. So this is 1/2 times 0 minus -1, which is just 1/2 times 1, or 1/2. So this is called substitution or U sub, and this is what we're going to work on next week. It's a little bit tricky. And one of my favorite things that I've posted for you guys, I've posted lots and lots of stuff in the modules. One of my very favorite things in there I'd like you guys to take a look at is a little explanation of why we need to change bounds. Actually, maybe I just put that on my calc too. Yeah, okay. Let me bring that in for you guys too, because you will like that now. Look, we're here. Modules. Here it is. So why we always need to change bounds when substituting indefinite intervals. I'll add this to your modules here. But that is it from me for today, guys. I hope you have a lovely rest of your day. Take a look at this thing in the modules that I'm posting now when you get a chance. And yeah, that is all. I will see you guys next Monday. On Monday, we will formally go over section 5.5. And then after that, we will start talking about areas between curves, which will be our last topic. All right, I'm gonna go ahead and end the meeting here. If you want to talk, you can always come by office hours. Otherwise, I'll see you on Monday. Take care, guys.